Okay, this is the last session for the IoT track, and we're going to hand over to Mance Harmon from Swirlds, where he's going to give us a glimpse of the future of IoT and blockchain technologies.
Well, good morning. So what I plan to present this morning is going to be forward-looking. This is sort of a vision for how the world of IoT can benefit from blockchain. And I'm going to start by describing blockchain in a way that perhaps you haven't heard before. This is, so by the way, Swirlds is a tech startup. My prior life, my job before joining Swirlds was with Ping. I was the head of architecture and labs for Ping. And Swirlds came along as an opportunity. And so some of this reflects the thought that I had while at Ping of what role does identity play in the world of blockchain. So with that, let's get started. What is a distributed ledger? I'm going to talk about this in terms of databases, and I'm going to build up a conceptual notion of the value of distributed ledgers by talking about what databases do. A database, you know, the simplest view of a database is you have an application that is writing and reading from a master, right? So obviously there's a little problem here in translation with the graphics, but it should be fine. From that, you can build a slightly more complex solution by creating a slave off of the master where the master replicates its transactions over to the slave, giving it some better reliability. If the master goes down, the slave can be promoted, and the application then can use the slave in a failover context. If we want to add a little more complexity, we can have multiple parties reading from the slave and the master, where you have the slave simply handling read requests, and all write requests are going to the master. So we're still in a master-slave architecture here. And then finally, we might have two masters, where we have both of these being hot or active in the sense that both databases are processing both write transactions as well as read transactions. And then those transactions potentially have to be deconflicted. If you're writing to the same location in the database at the same time, there is the question of who wrote first. And so you have to have some mechanism that will decide the answer to that question and make sure that both of the masters apply the write in the same order, okay? And then you can add another stack, full stack, application writing to a master where the write transactions are being replicated across all the masters, all the writes are being deconflicted. Again, this is what we would call this a single-party database with a multi-master architecture. What's unique about the world of blockchain is this. It takes multi-master technology from being managed by a single party to now each master being managed by a different legal entity, a different administrative control, right? This is new. This is what blockchain brought to the table. Now, when you hear the word blockchain, you probably think Bitcoin, right? Well, Bitcoin is just an application, right? That's all it is. Think of the cryptocurrency at the application layer. Fundamentally, what's happening here is that there is a multi-master database. In the case of Bitcoin, thousands of masters, and the consensus mechanism that undergirds the technology ensures that all of the write transactions are being deconflicted and all the masters stay in sync. So what do you need to think about? What are the considerations when evaluating technologies, multi-master technologies that have that security model, right? Or need to address the security concerns when you have multiple masters for multiple administrators, different legal entities managing each master. Well, obviously you want to talk about performance. Transaction throughput and consensus latency is an issue not just for multi-party databases, but for single-party databases that have a multi-master architecture. You want to talk about security? No single party should be able to do any of these three things if we're in a multi-party database. No single party should be able to modify transaction history or prevent the flow of transactions across parties or unfairly influence the order of those same transactions. These are concerns that are unique in some ways to the multi-party database problem. With the exception of the middle one, you want to, even in a single-party database, well, I guess technically, in a single-party database context, if you have disgruntled insiders, potentially you could have to deal with this in a multi-master deployment, these same types of concerns in a multi-master deployment. But maybe you worry less than you would if it's a multi-party database where each master is being run by a different legal entity. But these are the security concerns of a multi-party database. And then scalability. You want to be able to allow hundreds or thousands of participants, in other words, hundreds or thousands of masters that are still performant and address these security concerns. The way that this is done, typically for the old school algorithms, the multi-master databases that don't address multi-party, is through a leader-based process. All the masters will send transactions to an elected leader. The leader will put them in order and send them back out to all the other nodes. Blockchain addressed it differently. It made it such that each master is in a competition for the privilege of publishing a block of transactions. And it's basically solving a hard crypto puzzle. And on average, it takes 10 minutes to solve this crypto puzzle, and that's calibrated based on the number of masters that exist in the marketplace. And so about every 10 minutes, one master solves the puzzle, and then they publish their block of transactions to the rest of the masters, and that's how they order the transactions. It's extremely expensive because they're just wasting electricity trying to solve this crypto puzzle. There is another approach. It's a voting-based approach. I won't go into the details of it in deference to time here, but it's completely impractical because of the amount of bandwidth that's required. Basically, each master is asked to vote on a yes or no question. They send their vote out to everybody. Everybody has to then send acknowledgments of receiving the vote to everybody. And the number of votes and messages just to answer a single yes-no question as opposed to an array of yes-no questions just explodes. And so they're not used practically in the market. What HashGraph does is eliminates the need for sending those votes across the network. It makes it possible to be extremely efficient in terms of the voting algorithm part of this. It makes it such that there is no leader. And the leaderless aspect of this is important when it comes to the security concerns that I just previously discussed. It's not possible to execute a denial of service attack on a leader if a leader doesn't exist. If there's no leader that is elected to order the transactions, put the transactions in order unilaterally, and send them back out to all the other participants, then you don't worry about the leader unfairly influencing the order of transactions. So this approach, a leaderless approach that effectively uses voting-based algorithms without the need to cast votes over the internet, is a very efficient way of solving the same problem that blockchain does, where there are multi-parties participating in this shared data layer. So what does this have to do with self-sovereign identity and distributed ledger technology? This talk is not about self-sovereign identity, but it is important just to have a little bit of context. Basically, the idea is that each individual or user is going to have control of their identity, meaning that they create a key pair, a public-private key pair that they own, that they control, and then there are attribute providers, issuers, that will create sets of attributes. They will do identity proofing on the user, And once the identity proofing is complete, they will sign a bundle of attributes, and that attribute bundle from that attribute issuer is attached to that key pair. And then the user makes the decision when accessing a relying party what attribute bundles to provide the relying party. So the user has control in this context. Now, there are different ways of achieving this, and those attribute bundles may be stored on a phone that's carried by the user. Maybe in some cases, certain attributes are stored in this shared data layer that's public. There are various ways, various approaches of solving this, but that's the general idea. And so what's the value proposition of this relative to a centralized architecture? Well, it scales better in some ways. It doesn't empower a central authority. It's a distributed infrastructure. It's resilient to denial of service, has better reliability. It's got DDoS resistance. Identity proofing is leveraged by the entire network. So this key pair, whenever the user proves their identity to a new attribute provider, that attribute provider is signing the attribute bundle, and then the user has all of these signed attestations or signed claims, would be a better word, verifiable claims for these attributes. The fact that this one identity, this one key pair has multiple verifiable claims associated with it means something in terms of how much you can trust that given identity. Relative to a peer-to-peer architecture where the user just has their phone and they carry around their identities in the phone along with the verifiable claims, part of the value that's provided here is that some of the distributed ledger technologies out there can provide the denial of service resilience, but they also, if the credential issuer, if the issuer of the attributes decides that they don't want to be involved in the revocation process. If I go to Salesforce and give Salesforce an attribute bundle from whomever, my employer, say IBM, and IBM doesn't want to have to manage the revocation query that's coming from Salesforce to determine whether or not those attributes are still valid, I want to outsource that, then it would be better to have that as a distributed architecture rather than run by a single legal entity. So there's value in having a distributed revocation resource out there that handles this function for this architecture. Okay, what about privacy? You know what? In deference to time, I'm going to just skip this for a moment. There are ways of addressing privacy concerns that might be associated with this approach to identity. Is it possible for the relying parties to talk to each other and collaborate to understand and figure out who you are? How do you address anonymity? I'm not going to talk about how that works, but just to say that it has been addressed by the industry and there are solutions to those problems. And here is a brief list of some of the organizations that exist today that are directly addressing I'll call it the initiative to achieve self-sovereign identity on a global scale. Okay, what's this got to do with IoT? Let's talk about IoT use cases. Here are a few. So vendors place bids to homeowners and building managers to replace dead light bulbs. Wouldn't it be nice if when my light bulb goes out in my house, I don't have to do anything? Automatically, some number of vendors that I've chosen bid on the opportunity to replace that light bulb. Sort of a reverse auction process. Or I'm driving my Tesla down San Francisco. I don't have a Tesla, hypothetically. I'm driving my Tesla downtown San Francisco, and I need to find a charging station. And I want my car to have the right to go and find that charging station and take me to the charging station that meets a certain set of policies that I've already described to the vehicle. Or a certain company wants to purchase electricity directly from a solar grid, or an analytics center wants to pay consumers a specific demographic for their Fitbit data so that they can do something with it in a study, right? And there are a whole bunch of these types of forward-looking IoT use cases that are really interesting, but we can't achieve them today. And let's talk about why. So what is the long view? If from an identity perspective, given the context and the background I've just described, what would an architecture look like for addressing identities in the long term, not just human, but thing identities as well? Well, first, we have this distributed ledger technology, and we're going to store on it or using it some combination of identities and attributes or other metadata that might be associated with these without talking about specifics. There are these two layers that are supporting self-sovereign identity flows and use cases, as well as sort of traditional market-accepted identity protocols, SAML, OAuth, OIDC. But we also need to address things. And so what's interesting is what these use cases have in common. What do these use cases have in common? In normal identity flows, it's assumed that we're starting with an identifier, that we have an identifier associated with the subject, and we want to look up something about that subject. We're wanting to look up attributes, etc. If you notice, in these use cases, we don't have an identifier to start with. The vendors that want to place bids to a homeowner to replace the light bulb, they don't really care about the identity of the light bulb, right? What they care about, what I care about, are the services that things provide. The Tesla vehicle doesn't care about the identity of the charging station. The Tesla vehicle wants to query some service that says, return to me the list of charging stations that meet a certain set of criteria that I have defined. It's true for all of these. You don't start with an identifier. You start with a query on a set of IoT services that are provided to find those things that provide the services you care about. It's very different, right? The services that IoT things provide are what's important, not the identity of the things themselves. So what does that mean for us here? Well, we have IoT as a set of flows and use cases that need to be addressed, but we're focused on services when it comes to the use cases associated with IoT, not even necessarily attributes. I guess one could make the argument that the services they provide maybe are a special class of attribute. That's possible. But we don't start with an identifier. And that has implications for the data structure that is being used to store the information. It's not a key value store, right? It's not a key with a JSON object that's attached to it that describes the attributes that are associated with the identifier. We need to be able to execute general purpose queries of arbitrary complexity that narrows down the things that have the services that we care about, which is different than what we've done in the past. And then you could apply that same logic not only to things, but to platforms that have APIs. The APIs provide services that we would like to be able to write applications that use, and sort of, a mashup of services provided by platforms through their APIs, perhaps using IoT things as well. So we have people and things and servers and the identity of all that need to be addressed in this future architecture that addresses all the use cases. So what is required for IoT to reach its full potential? It's this: public markets for IoT services. We need the ability to have low friction human-to-thing and thing-to-thing commerce right? We need to be able to pay microtransactions to things and consume the services that they provide in a manner that's very different than the world of IoT today. In the world of IoT, the applications and the infrastructure and the things are all vertically integrated. And when things are added to the system or provisioned to the system, the identity of those things are added to the application. The application knows the identifier for all the things it cares about. Well, okay, that's good for version 1, Gen 1. Gen 2 needs to make it possible to have thing markets, service markets, where the application developers and the thing developers all can benefit in sort of an eBay of thing services, but in a public infrastructure context, not run by a single company. That won't happen, but in a transparent architecture that can be built using the security model that's afforded to us by, quote, blockchain or distributed ledger technology with next-gen algorithms. So how does this work? Let's talk about Gen 1, 2, 3, and 4. We started with cryptocurrencies. It quickly became apparent that we can use blockchain to store more than just financial transactions between Alice and Bob paying a Bitcoin from one to the other. We could store arbitrary information in this distributed ledger, if you will, rights, ownership rights to other assets. And then we needed some way of making it possible for there to be complex agreements associated with the transfer of those ownership rights, maybe using the cryptocurrency. And so we added smart contracts to the stack to make it possible to scale up. The obvious next step is markets. We want to be able to match those that want to engage in commerce by fairly connecting producers and consumers, or buyers and sellers that want to work together to execute smart contracts for the transfer of ownership rights, perhaps using a cryptocurrency. And that is what enables the markets, distributed markets of things, services, where the grease that sort of makes all of this possible is the cryptocurrency that supports microtransactions, that creates the thing economy. Matching, fairly matching in a distributed fashion, not run by a single party or a single entity, but in a public distributed infrastructure that is fair, matching producers and consumers to engage in this IoT economy. That technology exists today. The capability to build this exists today. Of course, it doesn't. The infrastructure is not there today. But there's nothing that prevents us. There's no technological hurdle that prevents us from being able to do this today. The next generation of distributed consensus technology enables markets, that fourth generation that I described. So what's the takeaway? In summary, human identity, the identifier is known. A distributed ledger can be used for addressing identity use cases. When it comes to thing identity, the most interesting use cases require service discovery, where you don't care about the identity at the beginning, you care about the service, and you need to identify or find things that provide the service. And then from that, you dereference an identity, which means that you need distributed SQL. Blockchain, key value store, right? We need a distributed multi-master database that can scale on a global level, that uses SQL, that supports arbitrarily complex queries on this data store. And then IoT service markets. This is where IoT reaches its full potential. It has to be distributed and fairly matching the producers and consumers, meaning that you don't give preference. The part of the trust model is that if I engage in commerce in this economy, I'm not going to be susceptible to a third party giving preference to their best friends, or manipulating the order of transaction to unfair advantage that hurts me in some way. The cryptocurrency with micropayments is going to be critical for this economy. And of course, it has to be able to support the high transaction throughput with low consistence latency to scale to the number of IoT transactions that we would envision. Okay, that's it for the presentation. I think we have a minute or two.
I think you filibustered, so we've only got time for one very quick question.
Okay. Yes.
Can you go back to your previous slide? I'm a little bit not clear on what is the difference between human identity and thing identity in terms of the NoSQL and SQL? Why do you need
what I meant by this distributed ledger NoSQL, so for traditional identity applications, it's quite often the case that you have a key value store that doesn't require SQL, right? You have an identifier, and then attached to that, you have two columns in a database. You have an identifier, and then you have a blob of information there that may be structured that contains attributes information about this. You're not normally doing arbitrarily complex queries on the attributes to identify the user, right? You normally have the identifier first, and you use that to look up the attributes. With things, the use cases assume the opposite. You're searching a SQL database of things, services, and then from those services, you narrow down the things that provide the services, and there you get the identifier for the thing you care about. You flip it on its head, which means you need to be able to do complex queries against a relational database. Yes, right.
How do you trust them, because you're talking about sovereign identity. At the same time, you're talking about
The two infrastructures sort of exist in parallel. So sovereign identity would have claims issued by issuers that could be attached to things and or humans, but then we also need the services database that that allows us to do the complex queries we're describing, that returns a list of identifiers that we potentially then will use in a sort of a sovereign context. We could look up if there are attributes or claims associated with the identifier, we can use that identifier to get those claims. They really could be two separate parallel pieces of infrastructure that are complementary.
Mance.
But you have to have the services directory.
Fantastic vision that you presented. Thank you, Mance, and please join me in thanking him for the presentation. That concludes